So to introduce our next speaker, we have Dr. Volosin. He was the TESS project manager for the last 5 years, and he's the former lead for NASA's Humans to Mars. Please welcome Dr. Volosin, who's going to speak about the TESS.
Thanks. I wanted to seem vaguely relevant to this crowd, so if anybody knows Dave Beatty from JPL, Dave and I were the co-leads for the Humans to Mars study during Admiral Slatel's period and Dr. Griffin's period. So what I'm going to talk about, I've been on the TESS mission for 5 years now, from the beginning all the way through launch and commissioning, and we're just finishing up commissioning. So I wish I had some more results to share, but I will share what we have, so you'll be as up to date as anyone to have the most recent results from our PI. So, the whole goal is there a place out there like Earth, not only like Earth physically, but with life? And so I'm going to talk a little bit about one step in humans trying to figure out the answer to that question, and that's a transit photometry mission called TESS. It's a small explorer mission. It's about a $250 million NASA mission. We launched in April of this year. And our principal investigator is Dr. George Ricker, if anybody knows Dr. Ricker from MIT. And he cannot be here today. He's off in Switzerland. He got the gig over in Switzerland giving talks, so I am here. I'd much rather be here. So as Dr. Callis kind of talked about, the goal in exoplanet research, when I went to college, there was no such thing as an exoplanet. And I don't think we ever thought there would be a discovery of an exoplanet at that point. And that was in the 80s. So the first thing was, do they even exist? Can you determine if they exist? And that was proven in the 1980s to be true. So the first exoplanet discoveries were made. And then the next question was, well, how plentiful are they? Are there just a few out there? Or are they pretty plentiful? So we had a mission named Kepler that was talked about, and Kepler found quite a lot, and they're still culling through Kepler data to find more. And then the next thing is, well, how do we characterize them? Figure out what they're made out of, figure out if maybe they're habitable. And I'll talk a little bit about how the next series of activities have got to get you to the point where you can someday maybe determine, is there life outside of Earth? And so, as Dr. Callis talked about, the biggest thing that's been the tool for discovering has been transit photometry. So all you need is a really good photometer. You just need to be able to count photons very accurately, and you could detect that was Venus passing the sun. That's an easy one to detect. So that's inside our solar system, not so bad. But when these planets are farther away and they're very small, the drop in photon output that you receive at your photometer is very small, and so it takes a very accurate measuring device to find those planets. So this is best done from Earth orbit. So what you'll find out is, the Kepler mission was put in orbit for a reason. You get above the atmosphere. Counting photons is a lot easier at that point with good detectors. And so transit photometry gives you good detectability outside the atmosphere. But it doesn't tell you much except the relative size of the planet to the host star. And that's not that interesting. I want to know what it's made of. So as Dr. Callis mentioned, you want to do radial velocity follow-up to be able to determine the density by looking at the mass of the planets and their effect on the host star. So with any mission like a TESS mission, we not only fund a satellite, we build a satellite and launch it, we also fund ground researchers to use ground-based telescopes to do the radial velocity follow-up to get the mass of the planets, to determine the densities, because radial velocity follow-up work can be done from Earth. You don't need to go into space to do it. So it's a lot easier to spend your resources on the transit photometry part and then spend your remaining resources to do ground follow-up. So I won't go through this, just to say that we play this role, TESS does, in moving us from what Kepler did, showing that there are lots of planets out there if you look anywhere in the sky, to now looking more all over the sky to determine where some of the best candidates are for follow-up observations, trying to do direct imaging, trying to do spectra to be able to figure out the atmospheres of these planets. And I'll tell you a little bit about how we compare to Kepler and how we're trying to do something a little bit different. So this is TESS. So you see TESS isn't very large. The SpaceX team, and I'll show you a picture later, we launched on a Falcon 9. We're really small for a Falcon 9 launch vehicle. And so they called us small but mighty. So we're going to use that as our tagline going forward. And so I'll show you the orbit we're in. That's our big Ka band. We use 26 gigahertz transmitting data back to Earth every 2 weeks. For the 2 weeks in between, we stay stably pointed with better than 1-ish arc-second pointing stability over about a minute, so that we keep a large field of view, and I'll show you how big the field of view is, stably pointed for 2 weeks at a time. That's our cameras. Our cameras were built at Lincoln Laboratory up at MIT, and there's a fantastic team up there that not only built really great CCDs that are really, the sensitivity of those to be able to count individual photons so we can see Earth-sized planets orbiting around stars like ours, but also a great optical system. So we use a 7-element optical system to bring a 24 by 24 degree field of view. Each camera is 24 by 24 degrees into focus on the focal plane over a wide spectral area. So we a lot of okay, so here's our cameras. So when you see those cameras, the way they're laid out, they cover this portion of the sky that they overlap. So you have one up near the ecliptic pole, and then you kind of come down towards the ecliptic. You're kind of going, one on top of another. So I have a movie here in the next, to give you an idea. So what we're going to do is every month we focus on a different part of the sky. So we just finished our first month. And so for the first year, we focus on the southern hemisphere. Then we flip over, and in the second year, we're going to do the northern hemisphere. You see the Kepler field of view in the top, and then those are the K2 fields of view. So you get an idea of the difference in field of view using ours versus the Kepler instrument. This is how we stay stably pointed. We're in an orbit that goes out to the moon's orbit. And so every 2 weeks or so, twice a lunar month, we swing out to the orbit of the moon, and then we swing back to Earth, staying pointed with a couple arc-second accuracy all the way. We dump our data when we come by Earth, and we just did that here a couple days ago. We were at Perigee, and then we swing back out and do it again. The idea is to provide a stable platform with a good view of the sky for the entire period. So that orbit is stable for hundreds of years, and so it's a lunar resonant orbit. So the idea is that we circle between the Earth and the moon twice per lunar month. The moon is either on one side or the other side of the orbit during that time, so it's tugging at the spacecraft, and so it keeps the orbit perfectly aligned for hundreds of years. So we don't have to use propulsion to stay in the orbit. We do just have to unload momentum every orbit. We have momentum wheels on board for pointing. So in the end of the video, it highlights the northern and southern poles, right? That's where we do a lot of our observing. So just to follow up on that, here's what's happening. As you're walking those cameras around during a year period, yes, it is true that for some portions of the sky, you only observe for 1 month. And so you're only going to catch transits that occur during that month. But as you move more up towards the pole, you'll notice that that one camera at the pole is staying focused on the pole for an entire year. We flip around, we do the other pole for the second year. Now, the advantage of that is, if you're a fan of the James Webb Telescope, James Webb will have a continuous viewing zone where they can view for long duration either at the northern or southern pole. So we want to provide them with good follow-up candidates so they could do spectroscopy on some of the planets that we find. And so that's exactly why we set up the mission this way, is to kind of work jointly with James Webb, which weirdly enough, if anybody knows the history of James Webb was started at a point where there was no such thing as an exoplanet. So its mission had nothing to do with exoplanets. But now they are extremely excited to be able to use their spectrographs to be able to look at some of our planets and be able to try to do follow-up observations of atmospheric composition. So when you look at TESS, you say, well, we've done transit photometry from space. We had Kepler. Kepler found thousands of exoplanets. Aren't we done? We've done the research we need to do. This is the Kepler field of view. As Dr. Callis mentioned, it's a very small field of view, but we found plentiful amounts of planets in that field of view. That's the TESS field of view. You can see that we're not only observing the entire sky, but the key of TESS is we're looking in our solar neighborhood. So if you want to do follow-up spectroscopy, you cannot do it of a planet that's 3,000 light years away from Earth. You need to be a lot closer. And so our goal is to look at and find all the planets we can close to Earth, the solar neighborhood, 30, 40 light years and beyond. I know that's not real close, but 30, 40 light years and out to 300 or so light years. So that was a great plan. So what really happened? Let me give you as much as I can about what really happened. So in February, we packed up and I was in the chase car We drove TESS down to launch site at Kennedy Space Center. And for anybody who lives on the East Coast, it's always a welcome sight when you pass south of the border, headed down to Florida. And so I made sure we snapped a picture. That was probably the only time it was not raining on the trip. We were really worried that TESS had gotten wet because we had an extremely bad storm on the way down. Turned out TESS did not get wet, but all of our ground support equipment was in a second truck that wasn't sealed, and so it was soaked. So we did get it all dried out, did all of our pre-launch checkouts, including checking out the cameras. You can see the cameras there with their covers off being inspected for the last time. Problematically, our principal investigator was very worried that if the cameras had covers that deployed on orbit, they could get stuck and not deploy. So he said, I don't want to put any covers on the cameras. Now, we're inside a launch vehicle. If anybody's seen the inside of a fairing when they separate, we're inside a launch vehicle, and those cameras are all facing straight up, and they have lens hood covers that are like big catchers for any kind of debris that's going to fall. And so we were extremely worried. So we tried to go inside the fairing as clean as we could, assuming that we would get some debris falling when we were inside the fairing. So here's the fairing. So this is where SpaceX kind of laughed at us when they approached. So yeah, it's a little embarrassing. And if anybody knows Dr. Zurbuchen, Thomas Zurbuchen, who's the head of the science directorate at NASA, he came to our critical design reviews. This is like 2 years before launch. And he saw this as a diagram and, kind of an artist's concept of what we would look like. And he said, can we do anything about it? I'm embarrassed to launch that little thing on that giant rocket. And there just was no other mission that would be ready to fly with us. And so soon what you'll be seeing, Dr. Zurbuchen was out at the SmallSat conference last week. We're putting together a rideshare policy so that no mission will ever fly like this again. There will always be companions if you're a small mission. Now, we are in an odd orbit, so other payloads would have to be wanting to go where we're going. But yeah, SpaceX came over, encapsulated us, brought us over to launch site. This is launch day. We were extremely excited. It's actually launch day number 2. We scrubbed the first day due to some problems on the Falcon. I'm in the back there. That's the small but mighty pose. So Juliana Scheiman, who's over on the your left-hand side, I think, in dark, she's the SpaceX lead. She integrates all the NASA payloads. She came up with the small but mighty name for our mission, and so that's everyone posing in their Mighty Mouse pose or whatever that is. So that was launch day. Launch day went really well. That's my 2 deputies and the Vicki Moran and Matt Ritzko up in the corner. We're not actually standing there during launch. That's a replay at about 1 in the morning, about 8 hours after launch. We stayed in the control center. We weren't that casual about it. This is inside the fairing before separation. This is actually before a launch. We failed during pre-launch testing. The satellite failed one of its key tests. The star tracker said that it saw a bright white object and it would fail one of its own diagnostic tests. So we were going to have to scrub the launch. There are cameras inside the fairing. We had SpaceX send us video from inside the fairing. And you can see a little bit up towards the bottom on the, I think it's your right-hand side, there's a small white hole. There are vent holes in the fairing. And it turned out we had never done a test during daylight. So during daylight, the sun was shining into the fairing, and the star trackers were seeing a big, bright object which was coming in through the fairing. So we were able to clear ourselves for launch. And then if the video plays correctly, you'll see us separating. So that's us separating from the Falcon 9 and floating away. The empty seat is mine, because when you launch, SpaceX insists that you be in their building. So if anybody knows, the SpaceX building is actually off-site at Cape Canaveral, kind of out the south gate. So I was out there for the go, no-go. This is the rest of our team happily watching the satellite fly away. I don't know if we were that excited, because part of it was exciting to see that we separated. The other part was the terror of thinking we were actually going to have to operate the satellite now. So it was kind of scary. So a little test in orbital mechanics. This is our launch profile. I thought it was really interesting to go through. So we launch, we coast out over Africa. The second stage starts again, and it sent us out to a fairly high apogee. We started at only a 200-kilometer perigee, though. So at apogee, we do another burn so that we don't come back at 200 kilometers. We come back a little bit higher up. So you see us circling around. This is our first orbit. Come back towards Earth. We do a perigee maneuver on the second one to raise our apogee just about to the distance of the moon. So you'll see our second orbit takes us out to the distance of the moon. We do another perigee maneuver as we come around again to go even a little farther out. So the next orbit, we're going to go even past the moon. Moon's not at that position. And it's to align us. And if you wonder what it's like to do a gravity assist, we did one. We come up to the moon just at the right time. And watch this. The moon kicks us out of the plane significantly and puts us in an orbit that will not eclipse very often by getting out of that plane. So we go out to about 75 RE at our furthest apogee. And now we have to do one more maneuver when we come back around, and that's to adjust the orbital period so that it's exactly 2 orbits per lunar month. We want to get it precisely so we get that stable orbit over hundreds of years. So we do one last maneuver, and that's our TESS mission orbit. It's pretty incredible, and it is spot on what everybody planned. So the science of the mission will be greatly enhanced by the fact that we got in the exact orbit that we had planned. So that's our TESS orbit. There you go. Yeah, so it's, if anybody's ever worked with the flight dynamics team at Goddard Space Flight Center, and it's true out here at JPL as well, those folks are incredible in what they can do and simulate and be able to do. So this is our first image. So our first image came in about a month ago, and this is a small spot of the sky. You can zoom in. There's plenty of stars. And so again, let's compare ourselves to what Kepler does. Okay, so here's that little part of the sky you just saw in that picture, and that's one of our cameras. Our cameras each have 4 CCDs to make up a 24 by 24 degree picture. Okay, so that's the full picture we take. Every 2 seconds, we snap a picture of 24 degrees by 96 degrees of the sky. That's the Kepler field of view, just for comparison, over on the top. That's how big the field of view of our mission is. So I don't care if you have no interest in exoplanets, but you care about anything about astronomy that happens on time scales. Let's say you're looking for supernovas. If a supernova occurs in that large field of view, we will see the rise of the supernova and we will see it tail off. Not to get ahead of ourselves, but you might find out in the next couple of weeks we announce something like that. So if something like that happens, and you want to understand how supernovae occur, you can actually see the rise and the drop-off, and that tells you a lot about what's occurring in that supernova. Usually, you don't have a wide field of view camera like this with this good of image taking in space that's taking pictures every 2 seconds. So that's really the benefit of TESS. Now, this picture was taken during commissioning, so I'll apologize. Over to the side where the Kepler field of view is, what you see is some stray light. So there's some stray light in that picture. That was just the part of the sky we were pointed at. The Earth was a little bit close, so we had a little stray light. So let me show you another video. This happened during commissioning. I'm a big fan of Flash Gordon. Kind of looks like a Flash Gordon video. So we just happened to be looking at a part of the sky during commissioning when a comet flew by, a newly discovered comet. So you can see the comet coming around the sun. You could see the tail of the comet kind of swishing around as the comet flies by. On the MIT website, they even have a better video where you can see more of the tail. There's other things you can see in this picture. You can see some pulsing stars, some stars that vary in brightness. So you can see them kind of blinking on and off in this picture. And then if you could see, if you really focus closely, you see a bunch of white dots, mostly over to the far side as the comet's flying. The small dots are moving. Those are asteroids in the asteroid belt. So you see some asteroids moving across the field of view, and somebody who does asteroid research thinks they found a couple new asteroids. So they're following up on that research as well. Now, I'll blame Mars for screwing up the picture, because for all you Mars fans, Mars had a closest approach while we were doing this, and Mars light got into the camera. And that's the fuzz that makes it look like a Flash Gordon video, is Mars light coming into the camera. So, darn. So since what Dr. Callis showed is we know about the existence of plenty of exoplanets, but they're all in mostly one area of the sky. We don't happen to be looking in that area of the sky. We're looking in the southern hemisphere right now. Kepler's field of view is in the northern hemisphere. So what we did is we looked at other things that vary over time, like variable stars, like binary stars, just to calibrate ourselves against known information to see if our cameras were working right. So we got a lot of these plots, and we have a lot of these that, again, will be released soon of stars that people didn't know maybe had variability, that we were able to detect variability. So again, that'll all be coming out soon, but this was all done during commissioning. We did dump our first month's worth of orbit data, science orbit data. It's 115 gigabytes of data. And you can see the brilliant young scientists at MIT poring over the data there. And that's the one thing about exoplanet research. You can have the best computers in the world, but the human eye is still one important critical part of determining whether that really is an exoplanet signature in the data or whether it's a false positive. And so we still rely on some really brilliant young people to do that for us. So in the first orbit, the first 2 weeks, we found 1,500 transits. Now, a lot of those will end up being false positive if Kepler data is to be, to the norm, but maybe out of that, 100 to 200 will end up being real planets. We found some really interesting ones, which again will be released soon, star systems that don't look like our star system at all, and we found some small ones. And so, so stay tuned when we officially release results, which will be soon. You'll get to see a lot more. So again, just to compare ourselves, and this is a very similar diagram than what you saw before, but the y-axis is now Earth radius. So I've kind of zoomed in on that lower portion of the scale that you saw before. And the idea here is that these are all known exoplanets from Kepler data and from other sources. And the size of the bubble here, so you have similarly distance going on the x scale, radius on the y scale, but the bubble is the size of the planet versus the size of the star. So it's easier to detect when the planet is a good portion of the size of the star, harder to detect when the planet is very small compared to the size of the star. So you can see this is what's been found. It turns out that if you look over here again in the thousands of light years away, those exoplanets really aren't going to be capable, you're not going to be able to do follow-up research, spectrum research, direct imaging, they're just too far away. And you can see that most of the known exoplanets are just too far away to do any follow-up research. So let's add TESS to that same diagram. So this is what the TESS, the modeling and simulations based on the Kepler results and the perception of how planets will be distributed, this is where we'll be focused, and this is the part of this scale that we hope to fill in, which is dominated by small planets, dominated by planets closer to Earth, dominated by ones that can be followed up to look for atmospheres and research their atmospheres by James Webb and others. And again, just remember that if you care about astronomy and things that happen over short periods of time, that's what you would want to use TESS for. So we'll have not only an active program for exoplanets, we have a guest investigator program where people can propose to do all kinds of other research using TESS. Okay, so I think I've talked about all these. We're focused on bright stars, because bright stars are going to be good for follow-up research. They provide a lot of light to go through the atmosphere of a planet to be able to do photometry, or to be able to do, to do spectroscopy on them. And so that's our goal. And so we're in this unique orbit. We're collecting data. Performance so far has been excellent. We had a little bit of problem with our pointing stability. We've since resolved that, and so we're now able to stay pointed appropriately for our mission. And I was trying to tie this at the end to, so how does this tie back to being at a conference about Mars? And so I figured I've worked with Mars fans for years, and I am still a great Mars fan of human missions to Mars. This is one of the pictures from the Curiosity rover, where the Earth is one of the very small dots in the night sky. And my perception is, like myself, that those of you who care about Mars and want to go explore Mars are people who love adventure. And so someday you're going to be standing there on Mars and you're going to say, so where do we go now? And hopefully TESS will have provided you candidates for going further. And so don't forget about us. So that's TESS. If you want to look us up, we're out on social media. And yeah, I have a couple minutes if you have any questions. Anybody? I've stunned everybody. Yes, sir.
The 27 days a year that for a large part of the sky you can cover, is that the same 27 days every year? Or if the mission goes on for multiple years, is it a different 27-day period? And a second question related to that, if you obtain funding, indefinitely, how long could the mission be flying as far as durability of parts goes? I guess you don't have any consumables on board.
Sure, yeah, sure. So the first question is, for the first 2 years of the mission, we promised NASA that we do a full sky survey. So that means for each month, we'll move the cameras around in that sequence I showed. After the first 2 years, we could point anywhere. The limitations become where the Earth is at any given time, sun and the moon, so that we don't get stray light. But we could focus in one area of the sky for 6 months at a time, no problem for us. On the second one, we changed the way we dump momentum out of the wheels. We were only supposed to dump momentum once per orbit, but to keep the jitter down, we're now doing it 3 times per orbit. So that change in ops concepts, every time we dump momentum, we have to use thrusters, and that is the one consumable that we will run out of. We currently have 40 kilograms of fuel on board because we were so nicely put in our orbit, we didn't need to use a lot of fuel on our own. And so that 40 kilograms of fuel, we use 10 grams of fuel to dump momentum. So if you calculate that out, we've got a good bit of, 100 years worth of fuel left. So yeah, we're good. So.
We're over here to your left.
Oh, yes.
Sir, if I understand correctly, the vast majority of stars, the norm in the galaxy is red dwarfs. So based on that, does that affect you when you're looking for Earths in terms of habitable zones?
Sure, yeah. In fact, we're a little tuned to the red end of the spectrum specifically because of that, because we are staring for only a month at a time early on. So we are looking for planets Earth-like that would be closer in towards their star that might be orbiting in periods of 20 to 30 to 40 days. And so for this early survey, we are going to be looking at a lot of red stars. So we have every time, we have about 20,000 stars per sector of the sky that we specifically focus on. But it turns out that our pointing is so good that the hundreds of thousands of stars in that big picture, you could do photometry on any star in that picture. So we originally didn't know we'd be able to do that. But so right now you can use any stars. So, but we are a little bit more focused towards the red end of the spectrum for those specific ones. Okay. Yes, sir.
I might have missed this. I got here a little late, but did you actually catch any of the Kepler, the same planets that triggered the Kepler results and compare them with TESS? So
No, thank you. That's a great question. Our principal investigator wanted to look at the Kepler field of view as a way to calibrate the instrument. And NASA said, no, you planned on doing the southern hemisphere first. And I think I work for NASA. I think that NASA was a little worried that if we didn't get good results, that could say bad things about TESS. So they said, focus on the southern hemisphere. I think they were a little worried. Again, the results so far have been extremely good. So I think there was nothing to worry about. But Kepler's field of view is part of our viewing scheme for the second year of the mission. We will do the Kepler field of view.
We could probably take one more question.
Okay.
Any more?
I know. So the goal was to get away from the reaction wheels that were used on Kepler, but our reaction wheels had their own problems that induced jitter that we didn't expect. So there is no perfect solution for pointing stability using reaction wheels. Yes, sir.
Yeah, and it goes to the first lecture too. With all of this data coming in to say that planetary systems are so common, the silence with the people looking for intelligent life, it's kind of a paradox. So is there any, let's say, sharing of data so they'll know where to look for the sweet spots?
Hey, it's a great question. So think about TESS, right? My principal investigator calls it the People's Telescope. The goal of Kepler was the Kepler team looked at the field of view and they culled out of that field every planet they could find. Not so with TESS. TESS, 2 months after now, so 2 months after commissioning. So in another couple months, we will dump all of our data up at the archive up at Johns Hopkins in Baltimore. It will be publicly available. We will only find a small number of follow-up candidate planets for us to research ourselves, and then we'll leave it to the rest of the universe of astronomers to find all the rest of the planets. So it is not our goal to find everything that's in those field of view. It's just to provide an archive of really accurate data of the entire sky. I think I have to stop there. So, Bob, you have? Yeah. Yeah. Yeah.
Will you be able to find planets that have orbital periods of a year and 2 years?
Towards the poles, yes. Only partially, yes. Remember, for Kepler, they kind of relied on 3 transits to really prove that it was a planet. So even at the poles, we might only see 1, maybe 2 of a period that's similar to our Earth. And so what we're hoping is in an extended mission, we would end up spending more time on fields of view that had shown promise, while we've completed the first 2 years just to show from an all-sky survey standpoint where some of the most interesting candidates are. But yeah, I agree with you that in the long term, you would want to dwell in different places for longer periods. And we can do that. Okay? Hey, thank you very much for having me. Thanks.